Hello and welcome to the video for section 3.4. Alright, in this section we're going to talk about library of functions and we're going to talk about piecewise defined functions as well. Just a friendly reminder, you should definitely take notes while you watch the video, maybe print out the PowerPoints for the slides and take notes as you watch here. Now, this is a pretty short section. First thing we're going to talk about is graphing the functions listed and what this author calls the library of functions. Right? So the main idea here is that we want to be able to sketch a quick, rough sketch graph, right, of some particular functions without ever having to use graphing technology. That's ultimately what we're building up to here. Okay, and even though we have technology to sketch for us, and it's a wonderful tool, as we develop our tools of analysis, critical thinking, right, quantitative reasoning, this is going to help us develop part of those tools in our brain. We want to be able to sketch some graphs and think of like how these graphs might apply to some modeling situations, some applications, without having to use technology. So we'll begin this section here. So the first graph that we look at is what we call the absolute value function. And one thing I really like about what this author does is he plots a bunch of points for the absolute value function to just show you where the shape comes from, right? And then he reviews the conversations we've had earlier in this section, like where it increases, where it decreases, right? What symmetry it might have, right? Whether it's even or odd, and then where any like local maximums or local minimums might be. So a nice review of some prior conversations as we build onto that, and we just talk about the generic shape of these graphs. So this absolute value function kind of looks like a V, and we can see, here's a local minimum. We can see the graphs decreasing on this piece, increasing on this piece. Right? So when you talk about decreasing, right, we talk about the domain, right? So the graph is decreasing from negative infinity to 0, and we could see here's that decreasing interval, right? And then it's increasing from 0 to infinity. So from 0 out to infinity, the graph increases. So that general V shape is the absolute value function. Right? The second one we talk about is the constant function. Right now, obviously, this is a horizontal line, y equals b, right? And we're using function notation now, so we're going to say f of x equals b, right? Where b is that y-intercept. So there's zero slope, right? The slope is 0 for this line. Right? Technically, that's a review, and technically this is a review as well, right? The identity function is the line y equals x, and the reason they call it the identity function is because x and y are identical. So if x is 1, then y is 1, or if x is -1, then y is -1, right? So again, these lines are technically review for you here, but the author throws them in, right? These are general shapes you'd want to be able to know. So if I said sketch the line y equals x, you could rough quick sketch of that line without having to plot any points. Right? Then we have the square function, right? So the square function looks like a parabola is what it's typically called, right? You've probably seen this in your past somewhere. And again, he's plotting points specifically for you to show you where the shape would come from, right? So if I pick x equals -1, -1 squared is -1 times -1, which is +1, and there's that y value. And if I pick x equals -2, -2 squared would be -2 times -2, which is +4, so there's that y value. So if we were to plot points, we would get this general parabola shape. Right? Again, we can see this graph is decreasing, and then there's a local minimum, and then it's increasing, right? And that general shape there. Right? And there's the square function. Right? So ultimately, in this section, I want to be able to say to you, sketch the square function, and then you sketch that rough parabola shape without having to plot any points. Okay? And then, there's the information of the square function, right, we were kind of talking about. So the function is even, since it has symmetry to the y-axis, and it's decreasing on the interval -infinity to 0. Right? So again, from -infinity to 0, the graph decreases, and then from 0 to infinity, the graph increases, right? And then here's that local min value. Right? Right, and the next one is the cube function. So the generic shape of the cube function looks something like this. Looks kind of increasing over its entire domain here, right? There is no local max or min value on this graph, right? So the function is odd. It has symmetry to the origin. It's increasing over its entire domain, right? It never decreases. It does not have a local maximum value. Now again, what we ultimately want to do in this section is be able to say, you know, sketch the cube function, and you do a rough, quick sketch of that graph without having to plot any points or having to use any technology. All right, so the next function we look at in the library of functions is the square root function. All right. Remember that you can't square root a negative number. So if I plug -1 into this equation, square root of -1 is an imaginary number. So in this course, we're only going to graph real valued functions. So we're going to see that the square root function only exists when its domain is 0 or positive. All right. So again, for the shape of this graph, right, it's increasing over its entire domain. And again, the domain being from 0 to infinity. Notice we're including 0 in that domain, right, because square root of 0 is 0, right, but I can't square root a negative number. All right. There is no local minimum. Well, you know what? This is kind of funny. All right. So it says that there's a local minimum right here at this point, which I guess would be true. When you take a calculus course, they don't talk about this being a local minimum, but this book mentions that there is a local minimum there. All right, so we'll go with that. All right. Notice this function is neither even nor odd. Right, it has no symmetry to the y-axis, no symmetry to the x-axis. Okay. Again, ultimate goal in this section is for me to be able to say to you, sketch the square root function, and you sketch that rough shape of that graph. Then we have the cube root function, which looks a lot like the square root function, right? So here's kind of like the square root function here, and then it has a symmetry through the origin. So the difference between a cube root and a square root is I can have negatives under the radical, right? So the square root of 1 is 1, and the square root of -1 is also -1, right? So we can see that point plotted there, okay? Excuse me, I think I said that wrong. Right? Cube root of 1 is 1. The cube root of -1 is -1. Let's pick the number 8, although we don't see that on the graph. If we pick the number 8, it's a little easier to see. So if I take the cube root of 8, that's going to be 2, right? Because 2 cubed is 8, right? 2 times 2 times 2 is 8. So the cube root of 8 is 2. And then if you look at the negative, let's look at the cube root of -8. Right? So cube root of -8 would be -2, because -2 times -2 times -2 is 8, right? So -2 cubed is -8. All right, so anyway, so we can have negatives in the domain of that cube root function. So you can see the domain is all reals here, all right? And there's the basic shape of the cube root. Excuse me, and then the last one we look at is the reciprocal function. So the reciprocal function literally is the reciprocal of the x value. So if I pick x equals 2, the reciprocal of that is 1 over 2, or 1/2. Right? So the reciprocal function is defined as 1 over x. Okay? And there's the basic shape of that graph. So again, the main idea in this section is I want to be able to say to you, sketch the reciprocal function, and you know that the graph has this basic shape here. Right? And if we talk about domain of this function, remember that we can't have division by 0. So if I look at the graph, right, excuse me, the equation of this graph, I can't have division by 0. So x can't equal 0. So notice at x equals 0, we're getting no points on the graph. And a little bit later in the course, we'll talk about this specifically. This is called a vertical asymptote. But you don't see that term mentioned in this section, right? But just know that x can't be, x equals 0 can't be in the domain. So you notice how they write the domain like this. This is saying it's the set of all real numbers x such that x cannot equal 0. And this is what we call set notation, or set builder notation. All right. So the domain is all reals except x equals 0 in that case. Okay. All right. So if we were again in this section, main idea is to identify the shape with the name. Right. So if we were to identify the shape with the name, what would the shape of this graph be? All right, I waited for a second to see if you would tell me a guess, but of course I can't hear you, right? So, of course, you all guessed correctly. That is the square root function, right? So if I were to go back in the prior slides and I were to look at the shapes of the graphs, that's the shape of the square root function. Right? What's the shape of this? The shape of this graph? What is the name of that shape? All right, so a parabola would be the shape, but that is the square function. Okay. Then we have the absolute value function, that V-shaped graph. Right? And then this would be the cube root function, right? Now remember, the square root kind of looks like half of the cube root. Right? So there's our cube root function. Right? Let's see, then our next shape, that would be the cube function. So y equals x cubed would be that shape. And then we would have the reciprocal function. So those are all the new shapes. And then the review shapes, we had the horizontal line, which we call the constant function, right? And then we have the line with a slope of 1, which we call the identity function. We won't really do a whole lot of sketching of constant and identity functions in this section because you've done those in great detail in prior sections. All right? All right, so again, quick little quiz question here, right? If I give you this shape, what's the name of that shape of that graph? And that would be the cube function, right? So that looks like y equals x cubed. So the last outcome or objective for this section is to graph piecewise functions. Okay? Now here's the idea of a piecewise function is exactly what the name says. We're going to graph a function that comes in pieces, if you will. So the example that we're going to look at here is kind of a 3 pieces defined function. So we give one equation, and that's for this particular domain. We give another equation, and that's for this particular domain. And then we give a third equation, and that's for this particular domain. So 2 main skills that you are developing here in this conversation. One is, given a function defined in pieces, right? Given a piecewise defined function, how can I just plug x values in and get y values out? And then the second would be graphing, right? How would I graph a function in pieces? So we're going to talk about those 2 main things here, okay? So the first question being, given this function f of x, find these 3 different y values or function values, right? So if I'm going to find f at 0, right, the main question I have to ask myself here is, I'm given the value x equals 0, and I'm going to plug it into this equation, but which one do I plug it into, right? Do I plug it into this first equation and I get, 0 plus 1, which is 1? Do I plug x equals 0 into the second equation and get y equals 2? Or do I plug 0 into the third equation and get 0 squared, which is 0? Which one do I pick? And then obviously that question is going to be answered over here by the pieces of the domain. Right? So I'm going to ask, where does x fall? Right? Is x equals 0? Right? Is 0 greater than 1? And the answer to that question is no. So I don't use this equation. Right? Then I'm going to say, does 0 equal 1? The answer to that question is no, so I don't plug into this equation. And then, is 0 between -1 and 1? And the answer to that question is yes. So x equals 0 satisfies this piece of the domain, so I'm going to plug into this equation, and I'm going to get y equals 1 as the result for f at 0. All right, so f at 0 would equal 1, and that comes from this first equation. Okay. Then the second question here is find f at 1, right? So again, I could go through the same process, or I could say, is 1 greater than 1? The answer to that question is no. I don't use this equation. Does 1 equal 1? Yes, it does. So I use this equation. And notice there is no x in this equation, right? So whatever x I plug in, I'm always getting y equals 2. So in that case, we're going to say f at 1 equals 2. All right. And then the third question is f at 2, right? So again, I'm going to go kind of backwards here, right? I'm going to say, does x equal 2, right? Is 2 between -1 and 1? No. Does 2 equal 1? No. Is 2 greater than 1? Yes, it is. So I'm going to plug 2 into this equation, and I'm going to say f at 2 is equal to 2 squared, which would be 2 times 2, or 4 as a value. Okay? All right, now I'm actually going to skip letter B for a second because I think it's much easier to find the domain once I've graphed the function. I think I'm such a visual learner, that just is what makes sense to me. So I'm going to skip letter B. Let's do letter C, and then we'll come back to letter B. All right, now here's how I'm going to graph. All right, so I'm going to sketch a rough graph here by hand, and then we're going to put it together and make it look a little bit prettier. All right, so I'm going to graph all three pieces, and then I'm going to come back and I'm going to erase the pieces that I don't want. And it's going to be a little hard for me to use the digital tool here, so I'll show you how I'm going to do that in a second. So what does the line negative x plus 1 look like? So this is a line with a y-intercept of 1. So here's the y-intercept, and has a slope of -1. So I'm going to go over 1 and down 1, right? And then there's the graph of negative x plus 1. Now the reality is I don't want that entire graph. I only want that graph for this domain. So I want to go from -1 to 1. I only want to keep this portion of the graph right here. I'm going to delete the rest of it. Okay. And let me real quick just show you that what that would look like here. So what that would look like here is this piece. So here's the piece. Notice there's like a dotted line. So we erased, right? So here's the line negative x plus 1, and it's only valid from -1 to 1. Now I want to point something unique out to you here. -1 is allowed to be included in the domain. So I'm shading, I'm plotting that point here. X equals 1 is not allowed to be included in the domain, so I'm going to leave that as an open hole. So this is the first piece of my piecewise defined function. It's the line negative x plus 1. I've deleted the pieces I don't want. I'm keeping the piece that I do want. All right, and then the second equation. So the second equation is y equals 2. Now that's a horizontal line. So that's a horizontal line where y is 2. So if I sketch a horizontal line, right, there's that sketch of a horizontal line. That's a rough sketch of the constant function there. And I only want this constant function when x equals 1. So if I come out here to x equals 1, I only want that 1 point. When x is 1, y is 2. So you can see in our graph over here, when x is 1, y is 2, we're just plotting that 1 point. And we've deleted the entire horizontal line, and we've only kept that 1 point there. And then the last piece is y equals x squared. Right, so again, let me come up here, right? So if I graph y equals x squared, there's my rough parabola shape that we talked about when we did our library function. So you can see that here, right? Here's the library function that we're sketching. And we're deleting, the dotted part, right? So the dotted part is where I have deleted the rest of the parabola. All right, and I'm only keeping the parabola for x greater than 1. Right? So again, I'm deleting the parabola where x is less than 1, and I'm only keeping the parabola when x is greater than 1. So here's where x equals 1. I don't include the x equals 1 point because I'm only looking at x greater than 1. And then when x is greater than 1, I'm keeping the rest of that parabola. So there's the sketch of the piecewise function. All right. Now, obviously, the dotted lines aren't really a part of the graph. It's just a visual aid to help us with the sketching. Okay. So once I have the parts that I'm keeping, I think it's so much easier to determine the domain and the range. All right, so let's talk about the domain here. So notice there's nothing, right? Let me look at the graph. Notice there's nothing to the left of x equals -1, right? Nothing to the left of x equals -1. So the graph stops right here, and we can see that in the domain up here, right? So the graph's domain begins at -1, and then we have x's being plotted all the way up to x equals 1, and it kind of looks like x equals 1 wasn't plotted, but remember we have this point here. So x equals 1 is part of the domain, right? I get a y value out of it. And then when x is greater than 1, we start this graph. So the domain is all x's that are -1 or bigger. We're getting y's out of the graph. Okay, so let me switch to my little marker here. And the domain here is all x's greater than or equal to -1. Now remember, what we would typically do is we would write that in interval notation. I'd have -1 with a bracket, and then I would go out to infinity with a parenthesis. Okay? And then the same thing for the range. So let's look at the range visually here. So the range, it looks like the smallest y value I have is y equals 0, but I can't even really include y equals 0 because of that open hole. So it looks like y being greater than 0, not greater than or equal to. So I get y's on this graph that are greater than 0. And it looks like all of these, right? So I'm covering all of these y values here on the y-axis. All of these y values are getting plotted, but I just can't include 0. So the y's would be strictly greater than 0, right? And then as an interval, that means I'll put a parenthesis at 0 because I'm not including it, and then I'll go out to infinity. Okay. Okay, so this last example we're going to look at involves an application of piecewise defined functions. So remember, the beauty in math is that we can apply it to some real-world situations, and what we're going to look at in this case is a piecewise function and how it applies to like your power bill you might get for living, in your home or your apartment. So this problem says that in May 2006, Commonwealth Edison Company supplied electricity to residences for a monthly customer charge of a flat fee of $7.58 and then plus 8.275 cents per kilowatt hour for the first 400 kilowatt hours. And then 6.2808 cents for all usage over 400 kilowatt hours. So notice how this is a piecewise function, right? Because for the first 400 kilowatt hours, we're being charged one rate. And then for anything over that, we're being charged another rate, right? So let's say part A says, what's the charge for the first 300 kilowatt hours? Right? So if we're using 300 kilowatt hours, we're within that first 400. So we're going to take the 758 and then we're going to add 8.275 cents times the 300 kilowatt hours. Now before we do that, the only thing we want to be a little careful of here is there's a mismatch in the units. Notice how this flat fee is in dollars. This per kilowatt hour charge is in cents. So what I'm going to do is I'm going to convert the cents into dollars just by dividing by 100, right? So if I divide by 100, I'm going to get $0.08275 per kilowatt hour. Right? So this first cost, there's my calculation. So I got the flat fee of $7.58 and then the $0.08 times the 300 kilowatt hours gives me $32 and let's say 41 cents if I were to round. Right? Now part B says, what if you use 700 kilowatt hours? Now think about this, right? So if I use 700 kilowatt hours, the first 400 get charged at this rate. And then the 300 over that get charged at this rate, right? So my equation, I'm going to have this flat 758. I got the first 400 charged at that rate. And then I have the 300 over, right, being charged at that other rate. So, again, think about how we get that 300. We're going to take the X value that we were given, right, our usage. We're going to subtract out the first 400 that we already calculated here. Now, let's abstract. Letter C says create a function of X. So what if I use X kilowatt hours in a month? Right? And again, this is piecewise, right? So if my X is less than 400, well, less than or equal to technically, if X is less than or equal to 400, I'm using this equation here. So for any generic X less than or equal to 400, I'm using that first equation. Now, if X is more than 400, I have to take this approach, right? So here's what my equation would look like, right? If X is greater than 400, I'm going to take the 758 plus the, 8 cents for the first 400, and then I'm going to take the 6 cents for the X over 400, just like we did here, right? And then I just I multiplied this number out, I distributed this number, and I cleaned it up. Here's what that equation would look like if I cleaned it up. Okay, so ultimately, here's my piecewise defined function. So if X is 400 or less, I'm going to use this equation to find my cost. If X is greater than 400, I'm going to use this equation to find my cost. If we wanted to graph that equation, right, it would look something along these lines. So if I graph this line for the first 400, I get this graph, and then if I graph this line down here, right, this line right here for X greater than 400, I'm going to get that graph. All right, so there's a cool little application of piecewise defined functions. Now, even though these values are from 10 years ago, this is pretty close to what I pay. Now, I think I pay about 13 cents a kilowatt hour. Sometimes it fluctuates, depends on the time of day, actually. But we kept this model a little bit more simplistic and just assumed it was a flat rate throughout the entire day. right? All right, anyway, so as you have questions, please make sure you post them in the discussion board, and I'll see you in the next video.